Hi, I'm Mark Ashcroft. Let me show you the pulse response of a couple of PicoConnect 900 probes. Here I'm using the Pico 9311 20 GHz sampling oscilloscope in fully corrected time domain transmission mode, so that as I apply this 916 DC coupled probe, you get to see the response of the probe to an ideal 50 picosecond step transition. Let's get that saved to a memory trace and then swap this interchangeable head for a faster 926 divide by 5 probe. We could with equal ease swap the divide ratio or move to an AC coupled probe head. These probes have extremely low input capacitance, typically 0.3 picofarads, and thus have very low impact on the probe line. They are by far the least invasive probes of all that we have tested. The importance of low probe line impact is that as we probe, the downstream function will typically be uninterrupted. We change the signal amplitude slightly, but not significantly its timing or its pulse response. We also achieve really good pulse response from the probe and speed. Here we have a direct comparison of the two and can see the second blue trace to be somewhat faster. So we have here a 5 GHz probe and a 9 GHz probe compared. Here's a typical application for PicoConnect probes. This is a 3 GHz differential amplifier. One of its outputs, the through signal, displayed on the yellow trace. The other output terminated. Here we can freely probe around the inputs, outputs, logic controls and bias supplies. We can see that there is an impact of probing the inputs on the through yellow trace. Note the considerable peaking on those inputs. Now it isn't perfect, but that is known not to be a response of the generator. When we probed the yellow trace output, we saw a small fall in amplitude due to the probe's resistive load, but notably not a substantial change of step response, due for instance to any capacitive load. The other terminated output can be probed without impact to its partner. By driving with a sine wave, in a matter of minutes we can gather signal envelopes that occur during amplifier power down pulse, including response on the decoupled supplies. Likewise, here's a pulse input to the amplifier. Note that sluggish and unexpected response on the undriven input. Both outputs appear impacted by this, but not so much the bounce on the negative supply rail. In this case, I'm using 3 soldered-in probes to monitor a HDMI differential logic pair at 1.4 gigabits per second. The third probe provides a trigger from the data clock. This is not some ideal generator driving a cable, but a real-world data signal from a laptop controlling the sampling scope to that monitor that you glimpsed. AC coupled probes are used here to avoid diverting DC bias current from the TX port. As you witnessed, downstream function of the monitor was uninterrupted, and these 3 probes still don't cost as much as a single active probe to do this. Here we interface HDMI to a Teledyne LaCroix oscilloscope. PicoConnect passive probes have a single 50 ohm output and no control, correction or power interface that might lock their use to a manufacturer or even a family of oscilloscopes. And in this comparison of 2 probe step responses, we pit PicoConnect, uncorrected, against a manufacturer's S21 corrected active probe, both on the manufacturer's oscilloscope. There is good agreement between these 2 good probes, but the lower cost, less invasive Pico, the orange trace, is faster and less ringy. This 4 GHz Roden-Schwarz oscilloscope is somewhat short of bandwidth for a 5 gigabit per second USB 3 data stream. Nonetheless, we can see data flow and timing skew, not to mention high differential jitter and bit interval jitter. Here, divide by 5 probes keep us clear of oscilloscope noise floor, Single-ended probes permit D-skew at the oscilloscope, and again an AC coupled probe prevents bias bleed. Finally, let's return to browse around a broadband single-end to differential amplifier. This time we'll use Pico's new and fast vector network analyzer to look at S21 responses around signal control, bias and supply nodes of up to 50 volt DC bias. There is a -20 dB non-flat swing on the unused input of the amplifier, and we find a -45 dB plateau on a decoupled bias supply. Both of these are possible contributors to non-flat response.